In May of 2024, an astrophysicist named Jeremy Schnittman sat in front of a screen at NASA's Goddard Space Flight Center and watched a camera fall into a black hole. The camera wasn't real. The black hole was, or rather, it was a mathematically faithful reconstruction of the one sitting at the center of our galaxy, a supermassive object called Sagittarius A star, 4.3 million times the mass of the Sun, compressed into a region smaller than the orbit of Mercury. Schnittman and his colleague Brian Powell had spent 5 days running the simulation on a supercomputer called Discover using just a fraction of its 129,000 processors. The result was 10 terabytes of data, roughly half the text content of the Library of Congress, describing, frame by frame, what a person would actually see if they fell toward that object and crossed its boundary. The camera starts far away. The black hole is a dark circle against a field of stars surrounded by a thin, glowing ring of superheated gas. The accretion disk, matter spiraling inward at temperatures of millions of degrees. At first, the approach looks almost gentle. The stars behind the black hole bend and shimmer as their light warps through curved space-time. But the distortion is subtle, the kind of thing you might mistake for a heat haze. Then the camera picks up speed. At 31 million miles from the event horizon, it is moving at 41% of the speed of light. At 27 million miles, 51%. The accretion disk brightens in the direction of travel, an effect of relativity called Doppler boosting, and the background stars begin to crowd together, compressing toward the center of the visual field as though the entire universe is being funneled into a shrinking circle above you. The camera completes nearly 2 full orbits before crossing the event horizon. In real time, that takes about 3 hours, but to anyone watching from a safe distance, the camera would never appear to arrive. It would slow, redden, dim, and eventually fade from view entirely, frozen at the edge of the black hole like a photograph left in sunlight until the image bleaches away. That is not what happens from the camera's perspective. From the camera's perspective, the crossing is unremarkable. There is no wall, no barrier, no flash of light. The event horizon, the boundary beyond which nothing, not even light, can escape, passes without ceremony. And then, 12.8 seconds later, the simulation ends. The tidal forces of the black hole stretch the camera beyond the limits of material existence, pulling it apart atom by atom in a process that astrophysicists, with what may be the driest humor in all of science, call spaghettification. From the event horizon to destruction, 12.8 seconds. From destruction to the singularity at the center, the point where the laws of physics cease to function, the distance is 79,500 miles. That final distance is crossed in a fraction of a blink. When asked about the simulation afterward, Schnittman said something that stayed with me. He said spaghettification would be, quote, a cool way to go, but that he'd still opt for lying in bed surrounded by his loved ones. He was joking, but the joke carries an odd weight when you consider what the simulation actually showed, that the mathematics of general relativity, equations first written down in 1915, can predict, with frame-by-frame precision, what the last 12.8 seconds of a journey into a black hole would look like. We know what you would see. We know how fast you would be traveling. We know the exact moment the tidal forces would exceed the tensile strength of human tissue. What we do not know, what no equation, no simulation, no telescope can tell us, is what happens after. Not after you die, after the singularity, after the mathematics itself stops making sense. That gap between what we can calculate and what we cannot is where this documentary lives. A black hole is not the most violent thing in the universe. Gamma-ray bursts release more energy, supernovae are louder, magnetars generate stronger magnetic fields, but a black hole is the only object in the universe where the structure of reality itself, the relationship between space and time, between cause and effect, between here and there, breaks down completely. Inside a black hole, the coordinate that describes distance and the coordinate that describes time switch roles. The singularity at the center is not a place you travel to. It is a moment you cannot avoid, the way you cannot avoid next Tuesday. Every direction points toward it. Struggling to escape makes you arrive sooner, and outside the black hole, a distant observer watches you freeze at the edge, never quite crossing, your image reddening and fading across an asymptotic eternity, while from your own perspective you crossed that boundary minutes ago and have already been torn apart. 2 observers, 2 realities. Both of them correct. Both of them consequences of the same equations, written by the same theory, tested and confirmed by the same experiments that keep GPS satellites synchronized to within billionths of a second. The physics that adjusts your phone's map to account for the curvature of space-time around Earth is the same physics that predicts your body would be stretched into a thread of atoms as it falls toward the center of a black hole. The only difference is scale. On Earth, the effect is measured in nanoseconds per day. Near a black hole, it is measured in the complete dissolution of everything you understand about the universe. Tonight, we are going to take that journey, not as metaphor, not as thought experiment, but as a description, as precise as current physics allows, of what would happen to a human body, a human mind, a human experience, falling into the supermassive black hole at the center of our galaxy. We will start from the outside, where the physics is familiar. We will move inward, through regions where intuition fails, and we will end where the equations end, at the boundary of what science can say about the nature of reality. Some of what we encounter will be beautiful. Some of it will be disturbing in a way that is difficult to name. Not frightening, exactly, but vertiginous. The feeling of looking down from a height so vast that your sense of scale quietly collapses, and some of it will be genuinely unknown. Physicists do not agree on what happens at the event horizon. They do not agree on what happens to information that falls into a black hole. They do not know what the singularity actually is. These are not gaps in popular understanding. They are gaps in physics itself, open wounds in the deepest theories we have, and they have been bleeding for 50 years. But before we descend further into that darkness, if you find yourself returning to this channel, listening to the void between the stars as you fall asleep, consider subscribing. And if you have a moment, leave a comment. If science ever found a way to observe the inside of a black hole, would you want to look? The answer, I suspect, is the same answer humanity has given to every abyss it has ever encountered. Of course we would look. We always look. But to understand what we would see, we first need to understand how we arrived at this question. And that story begins not in a laboratory or an observatory, but in a trench. In the winter of 1915, while artillery shells fell on the Eastern Front, a German soldier sat down with a pencil and a set of equations that Albert Einstein had published only weeks before and solved them exactly. The solution described an object that should not exist. The soldier did not live long enough to learn what he had found. Carl Schwarzschild was dying when he solved the universe, not metaphorically. In the winter of 1915, Schwarzschild was a 42-year-old German astronomer serving as an artillery officer on the Eastern Front, calculating ballistic trajectories between shellings. He had volunteered for the war out of patriotism, a decision that, in hindsight, carries the particular cruelty of a man who could see to the edge of the cosmos, but not 6 months into his own future. Somewhere on the Russian front, between the noise of the guns and the mathematics of where the shells would land, he contracted pemphigus, an autoimmune disease that would kill him within months. And somewhere in that same window of time, he got his hands on a copy of Albert Einstein's newly published field equations of general relativity, the equations describing how mass warps the geometry of space and time, and did something that Einstein himself had not been able to do. He solved them exactly. Einstein had only managed approximations. The equations were notoriously difficult. 10 interlocking differential equations describing the curvature of four-dimensional spacetime in response to the distribution of matter and energy. Working with them was like trying to fold a map that fights back. Einstein had used rectangular coordinates and a series of simplifications to get answers that were close enough to predict the bending of starlight around the sun, close enough to explain a small anomaly in Mercury's orbit that had puzzled astronomers for decades. But Schwarzschild wanted the exact answer. He chose a spherical coordinate system, assumed a single non-rotating mass sitting alone in a vacuum, and worked through the algebra in what must have been the most surreal homework assignment in the history of physics. A dying man in a war zone calculating the precise shape of space-time around a perfectly spherical object. He finished the calculation and sent it to Einstein in a letter dated December 22, 1915. The closing line read, As you see, the war is kindly disposed toward me, allowing me, despite fierce gunfire at a decidedly terrestrial distance, to take this walk into this your land of ideas. Einstein, by his own account, was delighted. He had not expected his equations to yield an exact solution so quickly, if ever. He presented Schwarzschild's work to the Prussian Academy of Sciences in January 1916. The paper was published shortly after, and buried within it, like a knot in an otherwise clean grain of wood, was something strange. The solution behaved perfectly at large distances. Far from the central mass, it reduced to ordinary Newtonian gravity, the kind that makes apples fall and planets orbit. But as you moved closer, the mathematics began to strain. At a specific radius, a radius that depended only on the mass of the object at the center, certain terms in the equation went to infinity. The mathematics didn't just bend, it broke. For an object with the mass of the Sun, this critical radius worked out to about 3 kilometers. For the Sun itself, this was an academic curiosity. The Sun's actual radius is nearly 700,000 kilometers, so the critical zone was buried deep inside a region that the solution was never meant to describe. For an ordinary star, Schwarzschild's strange radius was irrelevant. You would never encounter it in nature. The physical matter of the star would always extend well beyond it, and the solution only applied to the vacuum outside. But what if it didn't? What if you could somehow compress all that mass, the entire Sun, every atom of hydrogen and helium and carbon and iron, into a sphere less than 3 kilometers across? What would the solution describe then? Schwarzschild didn't pursue the question. He likely considered it absurd. No known physical process could achieve that kind of compression. He returned from the front in March 1916, too ill to continue serving. He managed to write 2 more papers before the disease overtook him. He died on May 11, 1916, at the age of 42. The exact solution that bears his name, the Schwarzschild metric, would go on to become one of the most important results in the history of physics. But its strangest implication, the one hidden inside that troublesome radius, would take another 23 years to be understood. And even then, the man who understood it best would spend the rest of his career pretending he hadn't. Because the critical radius wasn't a flaw in the mathematics, it was a prediction. Schwarzschild's equations were describing, with perfect precision, the boundary of an object that most physicists, including Einstein, believed could not exist. The radius where the solution broke down would eventually be called the Schwarzschild radius. The object it described would eventually be called a black hole, and the surface at that radius, the invisible boundary where space-time curves so severely that light itself cannot climb back out, would eventually be called the event horizon. None of these names existed in 1916. The concept they pointed to was so far outside the frame of early 20th century physics that it would take decades of argument, resistance, and reluctant acceptance before the scientific community began to take it seriously. Einstein himself would publish a paper in 1939, 23 years after Schwarzschild's death, attempting to prove mathematically that such an object was physically impossible. The title was dense and forgettable. The conclusion was emphatic. The Schwarzschild singularity, Einstein wrote, does not exist in physical reality. He published it in October of that year, and in the very same year, with no reference to Einstein's paper and no apparent awareness of the irony, a young physicist named J. Robert Oppenheimer published the opposite conclusion, using Einstein's own theory to prove him wrong. The paper that proved Einstein wrong was 9 pages long. It appeared in the September 1939 issue of Physical Review under the title On Continued Gravitational Contraction, authored by J. Robert Oppenheimer and his graduate student Hartland Snyder. The timing is worth pausing over. September 1939. Germany had just invaded Poland. Britain and France had declared war. The world was tipping into the catastrophe that would define the century. And in Berkeley, California, a 35-year-old theoretical physicist was quietly demonstrating that when a sufficiently massive star exhausts its nuclear fuel, nothing in the known laws of physics can prevent it from collapsing forever. Oppenheimer was not, at that point, famous. That would come later, and for different reasons. In 1939, he was known within physics as a restless intellect. Someone who moved between fields the way other people move between rooms, picking up problems in nuclear physics, quantum mechanics, spectroscopy, and astrophysics with equal fluency, publishing solutions, and moving on before the dust settled. His attention had recently turned to the question of stellar death. What happens when a star runs out of fuel? Gravity, which the star had spent its entire life resisting through the outward pressure of nuclear fusion, finally wins. The star contracts. But how far? There were known stopping points. A star below a certain mass, roughly 1.4 times the mass of our Sun, a threshold calculated by the Indian physicist Subramanian Chandrasekhar, would settle into a white dwarf, its collapse halted by the quantum mechanical resistance of electrons refusing to be squeezed into the same state. A heavier star could collapse further, past the white dwarf stage, until it became a neutron star, an object so dense that a teaspoon of its material would weigh about 1 billion tons, held up by the equivalent resistance of neutrons. Oppenheimer himself, with his student George Volkoff, had calculated the upper mass limit for neutron stars earlier that same year. The number came out to roughly 3 solar masses. The question Oppenheimer and Snyder asked was the obvious one that almost nobody wanted to ask: what happens above that limit? If a star is too massive for electron degeneracy pressure to stop the collapse, and too massive for neutron degeneracy pressure to stop the collapse, and there is no other known force in physics that could intervene, what then? The answer was the thing Einstein had tried to disprove. The collapse continues, not to a smaller star, not to a denser remnant, not to any stable configuration whatsoever. The star falls through its own Schwarzschild radius and keeps falling, contracting toward a point of infinite density, leaving behind a region of space-time so warped that nothing, not light, not matter, not information of any kind, can escape from within it. But the truly unsettling part of the Oppenheimer-Snyder paper was not the conclusion itself. It was the discovery that the collapse looks entirely different depending on who is watching. Consider 2 observers. The first is standing on the surface of the collapsing star, riding it inward like a passenger on an elevator with a cut cable. The second is floating at a safe distance, watching through a telescope. For the observer on the star, the collapse is fast and total. The star's surface contracts, passes through the Schwarzschild radius without any perceptible change in the local physics, and continues inward. The passage through the critical radius takes a finite amount of time on the falling observer's wristwatch. There is no wall, no flash, no obvious marker of a boundary having been crossed. The star simply keeps shrinking, and within hours the falling observer, along with everything else on the star, reaches the center, where tidal forces beyond comprehension tear everything apart. For the distant observer, watching the same event, the experience is completely different. The star contracts, slowly at first, then faster. But as the surface approaches the Schwarzschild radius, something peculiar happens. The collapse appears to slow down. Light from the star's surface becomes redder, gravitationally redshifted, its wavelength stretched by the increasingly severe curvature of space-time. The star dims. Its surface seems to crawl toward the critical radius with agonizing slowness, approaching but never quite reaching it. In the distant observer's time, the star takes an infinite number of years to cross its own Schwarzschild radius. It never quite disappears. It just fades, reddening and dimming toward invisibility, frozen at the edge of its own collapse. 2 perspectives on the same physical event. One observer sees a star collapse in hours. The other sees it freeze for eternity. And general relativity says both descriptions are correct. Both are valid solutions to the same equations, applied to the same physical situation, differing only in the reference frame of the observer. This was the result that Soviet physicists later seized on when they named these objects frozen stars, because from the outside that is exactly what they appeared to be. Not holes in space, but stars suspended in the act of dying, their light reddened to the point of near invisibility, their collapse permanently stalled by the time dilation of extreme gravity. The term captures something real, but it captures only half the story. The other half, the half experienced by anything that actually falls in, is the half that Oppenheimer and Snyder uncovered, the half that Einstein refused to accept, and the half that would take the rest of the 20th century to be fully understood. Oppenheimer himself did not stick around to see it understood. Within months of the paper's publication, his attention shifted entirely. The war in Europe was accelerating. Physicists were beginning to grasp the military implications of nuclear fission. By 1942, Oppenheimer was directing the Manhattan Project at Los Alamos, building the weapon that would end one war and define the anxieties of the next. He never returned to the problem of gravitational collapse. As far as the historical record shows, he never published another word on the subject. Werner Israel, a physicist who later studied the history of black hole theory, described the Oppenheimer-Snyder paper as one of the most daring and prophetic papers ever published in the field. He also noted something harder to quantify, that the ideas it contained were so alien to the physics of the time that most physicists simply could not absorb them. The mathematics was not disputed, the logic was not challenged. The paper was just ignored, set aside, treated as a curiosity that belonged to a world too strange to worry about while the real world was busy tearing itself apart. Einstein and Oppenheimer both ended up at the Institute for Advanced Study in Princeton after the war. Einstein as a professor, Oppenheimer as the director. They talked from time to time, but neither of them, as far as anyone knows, ever discussed gravitational collapse again. The problem sat dormant for nearly 2 decades, waiting for a generation of physicists with fewer inhibitions and better coordinates to pick it back up. And when they did, the first thing they needed was a name, because Frozen Star described only what a black hole looked like from the outside, and the physics that mattered, the physics that would consume theoretical physics for the next 60 years, was the physics of the inside. For most of the 20th century, nobody could agree on what to call the thing that Schwarzschild's mathematics had predicted and Oppenheimer's physics had confirmed. The Soviets preferred Frozen Star. It was descriptive and cautious, a star that appears to hang forever at the edge of its own collapse, its light stretched into invisibility by the warping of space-time around it. The name was accurate from the perspective of a distant observer, which was the only perspective that mattered to physicists who doubted the interior solution had any physical meaning. If you could never observe what happened past the Schwarzschild radius, why bother naming what was inside? The Americans, meanwhile, leaned toward collapsed star, or gravitationally collapsed object, which had the virtue of being literal and the disadvantage of being something nobody wanted to say twice in a sentence. European physicists occasionally used Schwarzschild singularity, though this carried its own confusion. The surface at the Schwarzschild radius was not actually a singularity at all, as David Finkelstein demonstrated in 1958 when he showed it was merely a coordinate artifact, a mathematical illusion produced by an unlucky choice of how to label the points on the map. The real singularity was deeper at the center, where the curvature of space-time genuinely blew up to infinity. But by then, the word singularity had been attached to the wrong feature for 40 years, and the confusion lingered. What all of these names shared was a certain reluctance, a refusal to commit to the full strangeness of the object being described. Frozen Star emphasized the outside and pretended the inside didn't matter. Collapsed object was aggressively neutral, the kind of term you use when you don't want to scare the committee. Even Schwarzschild singularity kept the focus on the mathematics rather than the physics, on the equation's behavior rather than the object's nature. The name that changed everything arrived in the fall of 1967 at a conference organized by the Goddard Institute for Space Studies in New York City. The physicist John Archibald Wheeler, already one of the most influential figures in general relativity, a man who had spent years working through the implications of Oppenheimer's collapse scenario, was giving a talk about gravitationally collapsed objects. By his own account, he had grown tired of saying gravitationally collapsed object over and over. Partway through the lecture, either he or someone in the audience, the record is disputed, used the phrase black hole. Wheeler adopted it on the spot. He used it for the rest of the talk. He used it in print the following year. And within months the term had spread through the physics community with a velocity that tells you something about how badly the field needed it. Black hole did what none of the previous names had done. It committed. It named the object not by what it looked like from the outside, and not by the process that created it, but by what it did. It consumed. Light went in and did not come back. Matter went in and did not come back. Information went in and, well, that question would keep physicists arguing for the next half-century, and they are still arguing now. There is something worth noticing about the power of naming. For 50 years, the physics had been available. Schwarzschild's solution existed. Oppenheimer's collapse paper existed. Finkelstein's 1958 reinterpretation of the event horizon existed. All the mathematics was in place, and yet the object at the center of that mathematics remained for most physicists an abstraction, something that happened in equations but not in the sky. The name black hole collapsed that distance. It made the abstraction into a thing with behavior, with appetite, with an inside and an outside and a boundary that meant something permanent. Language did what mathematics alone could not. It made the physics feel real. And once the physics felt real, people started looking for them. The first strong candidate arrived earlier than the name, though its identification came after. Cygnus X1, an X-ray source in the constellation Cygnus, first detected in 1964 during a brief rocket flight carrying Geiger counters above the atmosphere, had been puzzling astronomers for years. It was too luminous in X-rays to be an ordinary star. The X-ray emission flickered on timescales of milliseconds, which constrained the size of the emitting region to something extraordinarily compact. By the early 1970s, a picture had emerged. Cygnus X1 was a binary system, a visible blue supergiant star orbiting an unseen companion so massive and so compact that the only explanation consistent with general relativity was a black hole of roughly 15 solar masses. Matter was being pulled from the visible star, spiraling into an accretion disk around the invisible companion, heating to millions of degrees and screaming in X-rays as it fell toward the event horizon. It was around this time that Stephen Hawking and Kip Thorne made their famous bet. Hawking wagered that Cygnus X1 was not a black hole, partly out of genuine scientific caution, partly, as he later admitted, as an insurance policy. If black holes turned out not to exist, he would at least win the bet. He conceded in 1990, paying Thorne with a one-year subscription to Penthouse magazine, a detail that tells you as much about the personalities involved as any physics paper could. But something even stranger had happened 11 years before either the bet or its resolution. In 1979, a French astrophysicist named Jean-Pierre Luminet sat down at an IBM 7040 mainframe computer, a machine that, by modern standards, had less processing power than a wristwatch, and produced the first ever computed image of what a black hole would look like. Not a photograph, obviously. There was nothing to photograph. Luminet calculated the paths of light rays bending around a black hole surrounded by an accretion disk, tracing each ray by hand through the equations of general relativity, and then rendered the result as a black and white image using India ink on photographic paper. The image showed a dark circle, the shadow of the black hole, surrounded by a bright, warped ring of light, with one side of the ring brighter than the other because the gas on that side was moving toward the viewer at relativistic speeds, its light boosted by the same Doppler effect that shifts the pitch of a passing ambulance. It looked, in broad strokes, like a lopsided glowing donut. 40 years later, the Event Horizon Telescope produced the first real image of a black hole, the supermassive object at the center of the galaxy, Messier 87, 6.5 billion solar masses, heavy 55 million light-years away. The image showed a dark circle surrounded by a bright warped ring of light, with one side brighter than the other, a lopsided glowing donut. Luminet's hand-drawn calculation, produced on a computer weaker than your phone with ink on paper, had been essentially correct for 4 decades. The mathematics knew what a black hole looked like long before any telescope was powerful enough to check. And 3 years after that, in May 2022, the same telescope collaboration released the image of the one that matters most to us. Sagittarius A star, our black hole, the one sitting 27,000 light-years away at the center of the Milky Way, 4.3 million solar masses, an event horizon about 17% as wide as the distance from the Earth to the Sun. The image was harder to produce than the one of M87 because Sagittarius A star is 1,000 times smaller and the gas around it changes on timescales of minutes rather than days, so the target was constantly shifting even as the telescope array collected data. The final image was an average of thousands of individual reconstructions, all consistent with the predictions of general relativity for a Kerr black hole, a black hole that spins. So the object has a name. It has been photographed. Its mass has been measured to 4 significant figures by tracking the orbits of stars whipping around it at thousands of kilometers per second. We know it is there. We know how heavy it is. We know how fast it spins, roughly. We know the diameter of its shadow. What we do not know is what it feels like to fall into it. And to answer that question, we have to stop looking at the black hole from the outside, the way astronomers and telescopes and distant observers always have, and start moving toward it. Imagine you are falling toward Sagittarius A star from a distance of about 100 million miles, roughly the distance from the Earth to the Sun. At this range, the black hole does not look like much. If the accretion disk were not there, you would see a patch of sky where the stars are slightly wrong, their light bent into faint arcs and duplicated images by the curvature of space-time, the way a glass of water on a table warps the pattern of the tablecloth behind it. The distortion is gentle. You would have to know what you were looking for to notice it at all. But the accretion disk is there, and it is visible from a long way off. A flat, diffuse structure of gas and dust spiraling inward, heated by friction and compression to temperatures that make the surface of the Sun look tepid. The outer edge of the disk around Sagittarius A star extends to roughly 100 million miles from the center, and even at its cooler fringes, the material glows in infrared and radio wavelengths. As you get closer, it resolves from a vague brightness into something with structure, filaments of superheated plasma, knots of denser material tracing the spiral arms of the inflow, the whole thing rotating at velocities that climb as you move inward. The inner edge of the disk sits at about 23 million miles from the black hole, roughly a quarter of the Earth-Sun distance, and here the gas is moving at a significant fraction of the speed of light, glowing fiercely in X-rays, its temperature measured in hundreds of millions of degrees. You are still a long way from danger. At 100 million miles, the tidal forces, the difference in gravitational pull between the near and far sides of your body, are negligible. You could orbit comfortably at this distance, the same way the Earth orbits the Sun, and the physics would be entirely Newtonian. Nothing unusual, nothing that a 17th century physicist could not have calculated with pen and paper. But you are not orbiting, you are falling inward. And as the distance closes, the first thing that changes is not what you feel, but what you see. The black hole's gravity acts as a lens. Light from stars behind the black hole is deflected around it, producing warped and duplicated images, an effect called gravitational lensing that has been observed countless times by telescopes studying distant galaxy clusters, where the gravity of an intervening mass bends the light of objects beyond it into arcs and rings. Here, close to a black hole, the effect is extreme. Stars near the apparent edge of the black hole's silhouette are stretched into bright crescents. Stars directly behind it can produce full rings of light. Einstein rings, they are called, though Einstein himself never particularly liked the idea. As you approach, the visual distortion grows. The star field behind the black hole ripples and swims, as though you are watching it through water, and the black hole's silhouette, the dark region where no light arrives because every trajectory that enters it is captured, grows wider, not just because you are getting closer, but because the bending of light around it means that the shadow appears larger than the event horizon actually is. The shadow you see is roughly 2.5 to 5 times wider than the event horizon itself, depending on the black hole's spin, because photons that pass close to the black hole are deflected so severely that even light that was never aimed at the event horizon gets swept into the darkness. Between the edge of the accretion disk and the event horizon, there is a region where the physics begins to deviate sharply from anything in ordinary experience. At a distance of 3 Schwarzschild radii from the center, about 36 million miles for Sagittarius A star, you pass the innermost stable circular orbit, the last distance at which matter can orbit the black hole without spiraling in. Below this radius, there are no stable orbits. Every trajectory is a descent. This is where the inner edge of the accretion disk terminates, and it is the boundary between the universe where orbital mechanics still works and the universe where gravity has the final word on every path. Closer still, At 1.5 Schwarzschild radii, roughly 18 million miles, you reach the photon sphere. This is the distance at which gravity is exactly strong enough to bend a beam of light into a circular orbit around the black hole. The orbit is unstable, like a ball balanced on the tip of a hill. The slightest perturbation sends the photon spiraling inward or escaping outward. But at this exact radius, light can and does loop around the black hole before reaching your eyes. If you could somehow hover here, which would require an engine more powerful than anything that has ever been built or theorized, you would be able to see the back of your own head. Photons reflected from your body would travel all the way around the black hole and return to your eyes from the front, carrying a deeply distorted image of whatever was behind you, the back of your skull, your shoulders, the nape of your neck, wrapped around the darkness like a reflection in a funhouse mirror. You would also notice something else. At the photon sphere, the sky has changed. The familiar dome of stars that you have known your entire life, the hemisphere of light above you, the ground or horizon below, has undergone a topological shift. All of the light from the external universe now arrives from above. Below you, there is only the black hole. No starlight reaches you from that direction because every photon that was traveling upward from below the photon sphere has been captured. The universe you came from has been compressed into a shrinking circle of light overhead, and beneath your feet stretches the most complete darkness that physics permits. You are still alive. The tidal forces at this distance, for a supermassive black hole like Sagittarius A star, are surprisingly gentle. The gradient of gravity across the height of a human body is not yet strong enough to cause discomfort. If you did not look out the window, if you relied only on the sensations in your body, you would feel nothing unusual. You are in free fall, and free fall, regardless of how fast you are moving or how close you are to the source of gravity, always feels like weightlessness. Einstein called this the happiest thought of his life, the realization that a person falling freely does not feel their own weight. It is the principle on which all of general relativity is built, and it holds here 18 million miles from the center of a 4 million solar mass black hole, just as it holds in an elevator on Earth when the cable snaps. The difference, of course, is that this elevator has no floor to hit, not in the conventional sense. What waits at the bottom is not a surface but a boundary, and beyond that boundary, the concepts of bottom and floor and distance will stop meaning what they have always meant. You are approaching at roughly 60% of the speed of light. In the NASA simulation, this is the point where the entire visual field has begun to shift forward, the stars and the accretion disk crowding together in the direction of your motion, brightened and blue shifted by the Doppler effect, while behind you the universe fades into a dim, reddened emptiness. The effect is called relativistic aberration, and at these velocities it is dramatic. You are no longer seeing the sky as it is. You are seeing it compressed, warped, blue shifted ahead and red shifted behind, the geometry of observation itself deformed by your speed through curved space-time. And ahead of you, growing wider with every passing second, is the event horizon. You cannot see it directly. It has no surface, no glow, no physical substance. It is not a wall. It is a boundary in the causal structure of space-time, a sphere defined not by what is there but by what can no longer leave. Everything that crosses it from the outside is permanently removed from the observable universe. No signal, no particle, no influence of any kind can travel from inside the event horizon to outside it. The speed required to escape exceeds the speed of light, and since nothing with mass or energy can move that fast, the interior of a black hole is, by the strictest definition physics can offer, a separate region of reality. You are 10 million miles from it, moving at 62% of the speed of light. From here, the accretion disk looks like a bright band wrapped around a void, and the photon rings, thin circles of light produced by photons that have looped around the black hole 1, 2, 3 or more times, are visible as sharp, nested arcs inside the disk's glow. And nothing hurts. You feel nothing. The most extreme gravitational environment in the observable universe, and your body registers it as a Sunday afternoon nap. That calm is about to end. Not because you are about to hit something, but because you are about to cross a line that the universe draws in absolute silence. No alarm, no sign, no sensation. And once you do, the meaning of space and the meaning of time will begin to come apart. 18 million miles from the center of Sagittarius A star, light forgets how to travel in a straight line. That is not quite accurate. Light always travels along the straightest possible path through space-time, which is the definition of a geodesic. But near a black hole, space-time itself is so severely curved that the straightest possible path bends into a circle. At exactly 1.5 times the Schwarzschild radius, a photon fired sideways, tangent to the black hole, not aimed at it or away from it, will loop all the way around and return to where it started. The orbit is unstable in the way that a coin balanced on its edge is unstable. The slightest deviation sends the photon either spiraling inward to be swallowed or escaping outward into open space. No photon remains in this orbit for long, but at this exact distance, for one perfect and precarious moment, light goes around. This is the photon sphere, and passing through it is the point at which the experience of falling into a black hole begins to depart from anything a human nervous system was built to process. Consider what you would see. You are falling feet first, which is the convention physicists use when they discuss this problem, partly because it simplifies the mathematics, and partly because there is something darkly appropriate about going into the unknown the same way you entered the world. As you approach the photon sphere from above, the visual field has already undergone significant distortion. The accretion disk is wrapped into strange shapes by gravitational lensing. The background stars are smeared and duplicated, and the dark silhouette of the black hole dominates your downward view. But at the photon sphere, a new optical phenomenon emerges. You begin to see photon rings. These are not the accretion disk itself. They are images of the accretion disk. Light that has orbited the black hole once, twice, 3 times or more before reaching your eyes. Each successive ring is thinner than the previous one by a factor of roughly 535, the number e raised to the power of 2 pi, and each is nested inside the last, forming an infinite series of concentric bright circles converging on the edge of the black hole's shadow. In principle, there are infinitely many of these rings. In practice, the higher-order rings are so thin and so faint that only the first few would be visible, each one carrying an image of the accretion disk from a slightly earlier moment in time, each image progressively more distorted and time-delayed. You are looking at the same object reflected back at you through multiple laps around a gravitational mirror, each reflection older and dimmer than the last. And among those reflections, if the geometry is right, is your own image. Photons that left the back of your head minutes ago have traveled around the black hole and are now arriving at your eyes from the front. The image is warped, stretched and compressed by the curvature, arriving from a direction that makes no intuitive sense. But it is physically real. You can see yourself from behind, not in a mirror, not through a camera. Through the fabric of space-time itself, bent into a closed loop by gravity so extreme that even the path of light has become a circle. I want to be careful here because this detail has a tendency to sound whimsical, like a party trick of general relativity, and the reality of it is something stranger. What you are witnessing at the photon sphere is the failure of one of the deepest assumptions your brain makes about the world, that light travels in straight lines and that the direction a photon arrives from tells you where the object is that emitted it. That assumption is the foundation of vision itself, the reason spatial reasoning works, the reason you can catch a ball or avoid a wall or judge the distance to a doorway. At the photon sphere, it breaks. Light that left the back of your head arrives from the front. Light from stars behind you arrives from above. Light from the accretion disk wraps around the black hole and reaches you from directions that have no correspondence to where the disk actually is. Your eyes are still functioning perfectly. The photons are still carrying accurate information, but the space-time through which they traveled is so distorted that the information, by the time it arrives, tells you something about the geometry of the universe rather than the location of objects within it. You are not seeing things that aren't there. You are seeing the shape of space-time itself, made visible by the paths light is forced to take through it. There is another change, subtler, but in some ways more disturbing. At the photon sphere, the sky splits. Below the photon sphere, no light from the external universe can reach you on an upward trajectory. Every photon that was climbing outward from below this radius has already been captured. The only light arriving from below is light that originated inside the photon sphere. And since you are falling through it, the only thing below you is the black hole itself, which emits nothing. So the view downward is darkness, not the darkness of a cloudy night, which is really just a scattering of visible light into wavelengths you can't see. This is the darkness of absence, no photons of any wavelength arriving from that direction, because space-time has arranged itself so that no photon can travel from there to here. Meanwhile, the view upward has changed too. The entire external universe, every star, every galaxy, every photon that was ever emitted in the visible cosmos, is now compressed into a hemisphere above you, and that hemisphere is shrinking. As you continue to fall past the photon sphere and toward the event horizon, the circle of light overhead contracts further. Stars that were spread across the full dome of the sky are now crowded together in a bright disk directly above, their light blue shifted by your increasing velocity, their images overlapping and blurring as the aperture through which the universe is visible narrows toward a point. You are watching the universe close above you like an eye. The gravitational time dilation at this distance is already significant, though you cannot feel it. A clock strapped to your ankle is ticking slightly slower than a clock strapped to your forehead because your feet are deeper in the gravitational well by the length of your body. On Earth, this difference exists but is laughably small, a few parts in 10 to the 16th power, far below the precision of any clock you could wear. Here, the gradient is steeper. The difference between your feet and your head is not yet large enough to notice, not yet large enough to cause physical distress, but it is real and it is growing. Your body, though you cannot feel it, is already living in two slightly different times. If someone were watching you from a great distance and could somehow resolve the image of a single human body against the glare of the accretion disk, they would see you differently than you see yourself. Your image would be slightly reddened, slightly dimmer, slightly slower. Each heartbeat would take fractionally longer to reach their telescope, and as you continue to fall, that reddening and slowing will increase asymptotically toward a limit that the distant observer can never quite reach the moment you cross the event horizon. From their perspective, you will never arrive. From yours, you are about to. In 1959, two physicists at Harvard, Robert Pound and Glenn Rebka, pointed a beam of gamma rays straight up from the basement of the Jefferson Physical Laboratory to a detector on the roof, a vertical distance of about 22.5 meters. When the gamma rays arrived at the top, their frequency had shifted. It was a tiny shift, a few parts in 10 to the 15th, but it was measurable, and it matched the prediction of general relativity with startling precision. The gamma rays climbing upward through Earth's gravity lost energy on the way, and since a photon's energy is directly proportional to its frequency, the frequency dropped. The photons arrived at the roof a little redder than they had left the basement. This was the first direct measurement of gravitational redshift on Earth. And the reason it matters here, falling towards Sagittarius A star at a significant fraction of the speed of light, is that the same effect, the same physics, described by the same equations, is what makes your body age at different rates depending on where you are in a gravitational field. Gravity does not merely pull objects toward each other, it changes the rate at which time passes. And near a black hole, it changes that rate so severely that the consequences stop being theoretical and start being, in a very literal sense, physical. You already live with this. Right now, as you listen to this, the global positioning system in your phone is accounting for gravitational time dilation. GPS satellites orbit roughly 20,000 kilometers above the Earth's surface, where gravity is slightly weaker than at sea level. Because gravity is weaker up there, time runs slightly faster on the satellites than on the ground, about 45 microseconds per day faster. The satellites are also moving at roughly 14,000 kilometers per hour, which produces a counter effect from special relativity, slowing their clocks by about 7 microseconds per day. The net result is that the satellite clocks gain 38 microseconds every day relative to clocks on the surface. If this difference were not corrected, if the engineers who designed the system had decided that 38 millionths of a second per day was too small to worry about, GPS positioning would drift by approximately 10 kilometers per day. Within a week, your phone would not be able to find the correct city. That is the effect of Earth's gravity. Mild, modest, barely there Earth's gravity, the gravity of a planet you can escape with a sufficiently large rocket and a full tank of fuel. The numbers change when you approach a black hole. At the photon sphere of Sagittarius A star, roughly 18 million miles from the center, the gravitational time dilation factor is already severe. A clock at the photon sphere ticks at about 58% of the rate of a clock far away in flat spacetime. If you spent 1 hour hovering at the photon sphere, which again would require technology that does not exist, someone watching from a safe distance would see that hour stretch to roughly 1 hour and 43 minutes on their own clock. You would not feel the difference. Your heartbeat, your breathing, the electrical impulses in your neurons, the molecular vibrations that constitute your body's chemistry, all of these would proceed at their normal rate as far as you were concerned. You would experience 60 minutes. You would age 60 minutes, but the universe outside would age 103. Closer to the event horizon, the effect grows without limit at 99% of the Schwarzschild radius, which is still technically outside the event horizon, still technically in the region from which escape is possible. The time dilation factor is roughly 10 to 1. 1 hour of your time corresponds to 10 hours of external time. At 99.9%, it is roughly 30 to 1. At 99.99%, 100 to 1. The formula contains a term that goes to infinity as you approach the event horizon, which means there is no limit to how extreme the dilation can become. The closer you get, the slower your clocks appear to tick from the outside, and there is no floor, no minimum rate, no point at which the effect saturates and stops. At the event horizon itself, the time dilation factor is formally infinite. 1 second of your time corresponds to an eternity of external time. This is where the mathematics becomes difficult to translate into experience. What does it mean physically for time to dilate by an infinite factor? It does not mean that time stops for you. From your own perspective, falling freely, nothing changes. Your watch ticks at 1 second per second, as it always has. You cross the event horizon in a finite amount of time, roughly 12 seconds for Sagittarius A star, measured on your own wristwatch, from the photon sphere to the horizon. The infinite dilation is not something you experience. It is something that happens to the relationship between your time and the time of the universe you left behind, and that relationship has consequences. Not for you. You are falling, and from your perspective the fall is smooth and uneventful. But for anyone watching you, a distant observer watching through an impossibly powerful telescope would see your descent slow as you approach the horizon. Your image would redden as the photons you emit lose energy climbing out of the gravitational well. Each successive photon would take longer to reach the observer, not because you have slowed down, you haven't, but because each photon has to climb a little higher out of a well that is a little deeper than the one the previous photon had to escape. The time between received photons stretches, your image dims, your outline softens, and in the observer's time the process never completes. You approach the event horizon along a curve that gets closer and closer but never touches, an asymptote in mathematical language, a line that the function approaches but does not cross. This is why early physicists called them frozen stars. From the outside, nothing ever falls in. The star's surface, the accretion disk, the infalling debris, all of it appears to slow, redden and freeze at the event horizon, accumulating in a dim, red-shifted shell that fades toward invisibility but never quite reaches it. In principle, every object that has ever fallen into a black hole is still visible, in some sense, to an outside observer, its last photons still propagating outward, each one dimmer and more red-shifted than the last, asymptotically approaching zero luminosity across an infinite expanse of time. In practice, the last visible photon arrives very quickly. For a black hole of a few solar masses, the time between the object being clearly visible and the last detectable photon reaching a distant observer is measured in milliseconds. For Sagittarius A star, it would be somewhat longer, but still brief, a final flicker, and then nothing. Your image does not freeze in any way that a real telescope could detect for more than a fraction of a second. The mathematical infinity of the asymptotic approach plays out, for all practical purposes, in the blink of an eye. But your body tells a different story. Between your feet and your head, there is a distance, roughly 1.5 meters, give or take, depending on how tall you are. And because your feet are closer to the center of the black hole than your head, they sit deeper in the gravitational well, and time passes more slowly for them. On Earth, this difference is vanishingly small, the kind of measurement that requires an optical lattice atomic clock, the most precise timekeeper ever built, to detect across a height difference of a single centimeter. Near a black hole, the gradient is steeper, much steeper. At the photon sphere of Sagittarius A star, the time dilation difference across the length of a human body is small but measurable by equipment far less exotic than an atomic clock. Closer to the horizon, it becomes significant. And at the horizon itself, the gradient between your head and your feet is, in a formal mathematical sense, the difference between one rate of time and a rate that is infinitesimally slower. A difference that, stretched across the tidal environment of the approach, translates into physical force. This is the connection between time dilation and tidal stretching. The reason your body will eventually be torn apart near a black hole is not because gravity is strong in the Newtonian sense. It is because time passes at different rates across different parts of your body, and those different rates produce differential accelerations. And those accelerations manifest as forces that pull your feet away from your head and compress your sides toward the center. The tidal force is, in a sense, the physical expression of a time gradient. You are not being pulled apart by a force, you are being pulled apart by time. But that violence is still ahead of you. At this distance, approaching the event horizon but not yet crossing it, the tidal forces on a human body near Sagittarius A star remain gentle. The black hole is large enough, its Schwarzschild radius wide enough, that the gradient of gravity across 1.5 meters of human body is not yet dangerous. For a stellar mass black hole, one of 10 or 20 solar masses, this would not be the case. You would have been torn apart millions of miles ago. Long before reaching the event horizon, your body stretched into a filament of individual atoms while still in the region from which escape was theoretically possible. But supermassive black holes are different. Their event horizons are so large that the tidal gradient at the boundary is surprisingly gentle. You can cross the event horizon of Sagittarius A star alive and intact, your body whole, your mind functioning, your watch still ticking at 1 second per second. You will not realize you have crossed it. There is no marker, no sensation. The event horizon is not a physical object. It is a mathematical surface defined by the paths that light can and cannot take, and it passes through you as silently as a time zone boundary passes through an airplane. The difference is that a time zone boundary is a human convention. The event horizon is a property of space-time itself, and once you have crossed it, the universe you came from, every star, every galaxy, every person you have ever known is no longer in your future. It is not accessible by any trajectory, at any speed, by any means. The separation is absolute, and it happened in silence. You're inside. There was no sound, no flash of light, no change in temperature or pressure or the rhythm of your breathing. The event horizon passed through your body the way dawn passes through a sleeping city, a boundary crossed without any local evidence that it was crossed at all. If you had not been tracking the numbers on a hypothetical instrument panel, the shrinking distance to the center, the climbing velocity, the deepening curvature of space-time around you, you would have no way of knowing that anything had changed. Einstein's equivalence principle holds here as firmly as it holds anywhere. A body in free fall does not feel its own weight. You are in free fall. You feel weightless. You have felt weightless since the beginning of the descent, and that weightlessness continues, unchanged, on the other side of the most consequential boundary in the observable universe. But something has changed. Something that no instrument can measure locally, because it is not a property of the space you are in. It is a property of the space you have left behind. The event horizon is not defined by what happens at it. It is defined by what can no longer happen across it. Before you crossed, light that you emitted, photons bouncing off your skin, infrared radiation from your body heat, radio waves from any transmitter you might have carried, could, in principle, escape to the outside universe. Some of those photons would have been gravitationally redshifted nearly to oblivion, stretched to wavelengths longer than the observable universe. But they could escape. The path existed. After you crossed, the path does not exist. Not because a wall has appeared, and not because the photons have slowed down. Light always travels at the speed of light, locally, even inside a black hole. The path does not exist because space-time itself, inside the event horizon, flows inward faster than light can travel outward. The geometry of the universe has rearranged itself so that every direction you might try to send a signal, forward, backward, left, right, up, curves inward toward the center. There is no outward direction anymore. The concept itself has become meaningless. The way north of the North Pole is meaningless. You can say the words, but they do not describe a place you can go. This is what it means for space-time to flow inward at the speed of light. The event horizon is the surface where that inward flow exactly matches the speed of light, so that a photon aimed directly outward hovers in place, making no progress, running at full speed on a treadmill made of space-time. Inside the horizon, the flow exceeds light speed, and even that hovering photon is carried inward. This does not violate relativity. Nothing is moving faster than light through space. Space itself is moving. The distinction matters, though it offers no comfort. You are being carried toward the center by the current of space-time, and no engine, no thrust, no physical force available in the universe can push you against that current, because the current is not a force. It is the shape of reality. 12.8 seconds. That is how long you have, according to NASA's simulation of a fall into a non-rotating black hole with the mass of Sagittarius A star. 12.8 seconds of proper time. Time on your wristwatch. Time in your neurons. Time as you experience it, between crossing the event horizon and being destroyed by tidal forces. Schnittmann's team calculated this for a camera falling feet first along a radial trajectory, and the number is not approximate. It falls directly out of the Schwarzschild metric, and it scales linearly with the mass of the black hole. For a black hole twice as massive, you would have roughly 25 seconds. For one half as massive, about 6. The universe gives you a countdown, and the length of that countdown is proportional to the size of the trap. What do you do with 12.8 seconds? Your body is still intact. The tidal forces at the event horizon of a supermassive black hole are, as we discussed, gentle by human standards. The gradient of gravity across the length of your body is present but not yet destructive. Your circulatory system is still functioning. Your eyes are still receiving photons. Your brain is still processing information, assembling a model of the world around you from the signals arriving through your nervous system. And those signals, for the first few seconds after crossing, are not dramatically different from what they were a moment before. The sky above you, the shrinking disk of blue shifted light from the external universe, is still visible, still contracting, still brightening as relativistic effects compress the incoming light into a tighter and tighter beam. The accretion disk, or what remains visible of it, is still glowing. You are still falling feet first. You are still in free fall. You are still weightless. But something has shifted in the structure of the space around you, and if you had the instruments to detect it, the change would be profound. Inside the event horizon, the Schwarzschild coordinate that physicists label R, the radial coordinate, the one that measures distance from the center, has changed its mathematical character. Outside the horizon, R behaves like a spatial coordinate. It tells you where you are. You can move toward the center or away from it. You can hold your position if you have enough thrust. The coordinate R describes a dimension in which movement is optional. Inside the horizon, R behaves like a temporal coordinate. It tells you when you are. And just as you cannot choose to move backward in time, just as Tuesday cannot be unvisited, just as a spoken word cannot be unsaid, you cannot choose to move in the direction of increasing R. The singularity at R equals 0 is not below you. It is ahead of you in the way that tomorrow is ahead of you. It is not a place you are traveling toward. It is a time you are traveling toward. And no trajectory, no acceleration, no conceivable action can prevent you from reaching it, any more than you can prevent next Wednesday from arriving. The physicist Sean Carroll put it as cleanly as it can be put. You can no more stop moving toward the singularity than you can stop getting older. There is a corollary to this that is easy to miss and difficult to accept. Since proper time, the time experienced by a falling observer, is maximized along a geodesic, the longest you can survive inside the event horizon is if you fall freely without resistance. If you fire your engines, if you struggle, if you try to slow down or reverse course, you shorten your remaining proper time. Every effort to escape brings the singularity closer. This is not a metaphor, it is a calculable result, derivable directly from the metric, and it inverts every survival instinct a human being has ever evolved. In ordinary life, struggling extends your time. Inside a black hole, struggling shortens it. The optimal strategy, the one that maximizes the number of seconds you have left, is to do nothing, to fall freely, to let go. The 12.8 seconds are ticking. And somewhere in those seconds, the exact moment depends on the mass of the black hole and the specifics of your trajectory, but it will come. The tidal forces that have been building quietly across the length of your body will cross the threshold from imperceptible to catastrophic. The gradient of gravity between your feet and your head will steepen beyond the tensile strength of bone, of tissue, of the molecular bonds that hold your cells together. And the process that astrophysicists named with such understated clinical detachment, spaghettification, will begin. The word was coined by Stephen Hawking, which tells you something about his sense of humor and something about the phenomenon it describes. Spaghettification, the process by which a three-dimensional object falling into a black hole is stretched along its direction of fall and compressed perpendicular to it, transforming from a body into a filament, elongating, thinning, drawn out like warm glass pulled from both ends until structure gives way and what remains is a thread. The physics behind it is older than the name. Tidal forces, the differential in gravitational pull between 2 points at different distances from a massive body, have been understood since Newton. They are the reason Earth has ocean tides. The moon pulls harder on the near side of the ocean than on the far side, and the difference in pull creates a bulge. They are the reason Jupiter's moon, Io, is the most volcanically active body in the solar system. Jupiter's tidal forces flex and heat its interior with every orbit. The same physics applied to a human body in the vicinity of a black hole produces a result that is qualitatively identical and quantitatively beyond comparison. Your feet are closer to the center than your head. The gravitational acceleration at your feet is therefore greater. The difference between these two accelerations is the tidal force, and it acts to pull your feet away from your head, to stretch you along the radial direction, the axis that points from the center of the black hole through your body and outward. At the same time, a complementary effect compresses you from the sides. Imagine yourself standing inside a cylinder that is being stretched vertically while the walls close in horizontally. The tidal force does both simultaneously. It elongates and it squeezes. The technical term is that the tidal tensor has positive eigenvalues in the radial direction and negative eigenvalues in the transverse directions, but the experience, long before anyone could describe it in the language of tensors, would simply be the feeling of being pulled apart. For the black hole we have been falling into, Sagittarius A star, 4.3 million solar masses, the onset of spaghettification does not happen at the event horizon. This is one of the counterintuitive features of supermassive black holes that distinguishes them from their stellar mass cousins. A black hole of 10 solar masses has a Schwarzschild radius of about 30 kilometers. The tidal forces at that horizon are immense, so severe that a human body would be destroyed at a distance of roughly 400 kilometers, more than 13 times the Schwarzschild radius. You would be spaghetti long before you got anywhere near the event horizon, and the last minutes of your approach would be a process of disintegration rather than experience. But tidal forces scale inversely with the cube of the distance and linearly with the mass, which means that for a black hole millions of times heavier, the event horizon is so much larger that the tidal gradient across a human body at that radius is mild. Sagittarius A star's event horizon is roughly 12 million kilometers across. At that scale, the difference in gravitational pull between your head and your feet at the moment of crossing is smaller than what you experience standing on the surface of the Earth. You cross the event horizon in comfort. You feel nothing. The destruction comes later, deeper inside, after the horizon has closed behind you and every possible escape route has ceased to exist. The 12.8 seconds that Schnittmann's simulation calculated represent the interval between crossing the event horizon and reaching the point where tidal forces exceed the structural limits of a solid body. Those seconds are not uniformly calm. The tidal gradient steepens as you fall deeper, following a curve that starts gently and then climbs with nauseating speed as the distance to the center shrinks. For the first several seconds, the forces remain manageable, uncomfortable perhaps, in the way that a strong acceleration is uncomfortable, a pulling sensation along your spine that you might initially mistake for the feeling of being on a very aggressive amusement park ride. But the tidal force does not level off, it does not plateau, it climbs, and the rate of climbing itself accelerates, so that the transition from mild discomfort to structural failure happens not over minutes but over fractions of a second. There is a result in general relativity, derived from the analysis of radial geodesics in the Schwarzschild metric, that says the following: regardless of the mass of the black hole, a falling body will be torn apart approximately 1/10 of a second before reaching the singularity. The mass of the black hole determines how long the fall takes, and it determines how gentle or violent the early stages of the descent are, but the final 1/10 of a second is universal. Whether you fall into a black hole of 10 solar masses or 10 billion, the destruction happens in the same narrow window at the very end, when the tidal forces spike toward infinity in the approach to the singularity. 1/10 of a second. In that window, the elongation of your body exceeds what connective tissue, what bone, what cellular structure can sustain. Your body stretches along the radial axis while being crushed inward from the sides, producing the shape that gives the process its name: a strand, a filament, a thread of matter falling inward, getting thinner and longer, the atomic bonds that held molecules together finally yielding under a differential in gravity that has grown beyond the scale of any force in material science. What was a body becomes a column of atoms. What was a column of atoms becomes a stream of subatomic particles. And then, but here the physics becomes uncertain, because then refers to conditions at or very near the singularity, where general relativity predicts infinite curvature and quantum effects that no current theory can describe. There is one more detail about the singularity that deserves attention because it contradicts the image most people carry in their heads. The singularity of a non-rotating Schwarzschild black hole is not a point, or rather, it is not a point in any spatial sense that the word point usually implies. The physicist Andrew Hamilton, who has spent decades building detailed simulations of the interiors of black holes at the University of Colorado, describes the singularity this way: if two people fall into a Schwarzschild black hole at the same time, but from different angular positions, one from above the North Pole, one from above the equator, they do not converge as they approach the center. They do not meet. The tidal forces channel each of them along the radial direction with such intensity that lateral movement becomes impossible. You cannot reach out your arm to touch someone beside you because the transverse compression has closed that direction of space to the width of an atom and then beyond. The singularity is not a place where all paths converge. It is a moment where all paths end separately, in isolation, each thread of falling matter arriving at R equals 0 along its own radial line, unable to communicate with any other. You die alone inside a black hole. Not in the colloquial sense of dying without company, though that too. In the geometric sense, the space-time around you has been deformed to the point where the concept of beside you has lost its meaning, where even the light from a companion falling a meter away could not reach you before the singularity claims you both. The loneliness is structural. It is built into the shape of the space itself, and then it ends. The body, the atoms, the particles, all of it crosses into R equals 0. The singularity, the boundary where the curvature of space-time becomes infinite, and general relativity admits that it has nothing left to say. What happens at the singularity is genuinely unknown, not unknown in the way that the interior of a distant planet is unknown. We could, in principle, send a probe and find out. Unknown in the way that the question itself may not be well formed, the way asking what happened before the Big Bang may not be a question with a coherent answer. The singularity is where the theory predicts its own failure. It is the mathematical equivalent of a sentence that ends mid-word. Whatever happens there, you will not be present to observe it. The version of you that was a person, that had memories, perceptions, a nervous system capable of constructing a model of the world and experiencing it as consciousness, ceased to exist 1/10 of a second earlier, disassembled by tidal forces into a stream of elementary particles threading inward along the radial direction. The singularity does not destroy you. The tidal forces already did. The singularity destroys the idea that there is a there for the destruction to have happened in. While all of that was happening to you, The crossing, the stretching, the dissolution, someone was watching from outside, and from their perspective, none of it happened at all. This is the part of the story that resists intuition most fiercely because it requires holding two contradictory truths at the same time and believing both. You fell through the event horizon. You were destroyed. Your atoms were threaded into a filament and pulled toward a singularity that general relativity describes as the end of space-time. This is what happened, measured on your wristwatch in your reference frame, according to the equations that govern the interior of the black hole, and simultaneously to an observer watching from a safe distance through an extraordinarily powerful telescope. You are still there, still visible, still hovering at the edge of the event horizon, your image reddening and dimming across an expanse of time that, mathematically, has no end. The physics behind this is the same gravitational redshift we discussed earlier. The same effect that stretches photons climbing out of a gravity well, shifting their wavelength toward the red end of the spectrum. As you approach the event horizon, each photon you emitted had to work harder to escape. It lost energy in the climb, and lost energy means lower frequency, and lower frequency means redder light. A photon that left your body as visible yellow light would arrive at the distant observer's telescope as infrared, then as microwave, then as radio waves of longer and longer wavelength. At the same time, the interval between successive photons increased. Your heart was beating at the same rate as always, once per second, let's say, but the photons carrying the evidence of each beat were arriving at the distant telescope with growing gaps between them. 1 second between the first two beats, 1.1 seconds between the next, 1.3, 2, 5, 30. The observer would see your heartbeat slow, your breathing decelerate, the movements of your body wind down like a mechanical clock running out of spring. This is not a visual illusion. The distant observer is not being tricked by bad optics or an imperfect telescope. The photons carrying your image are real. They carry accurate information about the state of your body at the moment they were emitted. The problem is that each photon was emitted from a deeper point in the gravitational well than the one before, and each one therefore underwent a slightly greater redshift, a slightly longer travel time, a slightly more severe loss of energy. The observer is assembling a perfectly accurate picture of you from photons that are arriving with increasing delay and decreasing intensity. And since the event horizon represents the point at which the redshift becomes infinite, where the energy of an escaping photon drops to zero and its wavelength stretches to infinity, the observer's picture of your approach never quite completes. You approach the event horizon along an asymptotic curve, getting closer and closer but never arriving. Your image dimming toward a final redness that fades below the detection threshold of any instrument, real or theoretical. In practice, this fading happens quickly. There is a common misconception that the frozen image of a falling object would remain visible at the event horizon for cosmically long periods of time, a permanent ghost plastered to the surface of the black hole. The mathematics says the image persists for infinite time, which is technically correct, but the luminosity drops exponentially. For a black hole of 8 solar masses, the timescale of that exponential decay, the time over which the brightness drops by a factor of about 2.7, is roughly 0.2 of a millisecond. The time between the object being clearly visible and the arrival of the last photon detectable by any conceivable instrument is measured in hundredths of a second. For Sagittarius A star, the timescale is proportionally longer because the black hole is much more massive, but the fundamental character of the fading is the same, a brief, rapid dimming, and then silence. So the ghostly frozen image that haunts the popular imagination, a face pressed against the event horizon for eternity, is real in principle, but invisible in practice. The last detectable photons arrive within moments of the crossing. After that, the event horizon is dark. Whatever fell in has, for all observational purposes, vanished. But vanished is a word that carries philosophical weight near a black hole. The atoms that made up your body still exist, in some sense. They have crossed the event horizon and are falling toward the singularity, where their fate becomes a matter of genuine scientific dispute. The The photons you emitted before crossing are still propagating outward, each one a little redder and fainter than the last, carrying increasingly stale information about a body that, by the time the photons arrive, has long since ceased to exist. And the gravitational influence of your mass has been added to the black hole's own, increasing its total mass by a quantity so small, one human body against 4.3 million suns, that the change is unmeasurable by any existing instrument, yet present in principle, a permanent alteration to the geometry of space-time around the black hole. You have left three kinds of traces: photons, dimming exponentially towards zero, a slight increase in the black hole's mass, detectable only in the abstract, and, this is the strangest one, an imprint on the event horizon itself, which, according to some interpretations of quantum gravity, encodes information about everything that has ever fallen through it. This last trace is the one that keeps physicists awake, because the classical picture, the one painted by general relativity alone, says that the information contained in your body is simply gone, swallowed by the singularity, erased from the universe, irretrievable by any physical process, and that picture is in direct conflict with one of the most fundamental principles of quantum mechanics, that information is never truly destroyed, that the quantum state of a system can always, in principle, be recovered from its future evolution. General relativity says the information is gone. Quantum mechanics says it cannot be. Both theories have been confirmed to extraordinary precision in their respective domains, and they disagree absolutely and irreconcilably about what happens to a body that falls into a black hole. This disagreement has a name. It is called the black hole information paradox, and it has been the single most debated problem in theoretical physics for nearly 50 years. Hawking himself, who first identified the paradox in 1976, spent decades arguing that the information was truly lost, that black holes represented a fundamental exception to the quantum mechanical principle of unitarity, a place where the rules broke down. He changed his mind in 2004, conceding a bet with the physicist John Preskill at a conference in Dublin, announcing that he now believed information was preserved, though he was not entirely sure how. The concession made international headlines. The mechanism remained unclear, and it remains unclear today. The paradox has not been resolved. There are promising directions: the island formula, quantum extremal surfaces, the idea that the event horizon itself may function as a kind of holographic record, encoding the information of everything that has ever fallen through it on a two-dimensional surface in the manner suggested by the holographic principle. There is the ER equals EPR conjecture proposed by Juan Maldacena and Leonard Susskind in 2013, which suggests that the interior of the black hole and the exterior radiation it emits are connected by quantum entanglement in a way that is geometrically equivalent to a web of microscopic wormholes. There is the AMPS firewall argument from 2012, which suggested that the event horizon might not be the smooth, uneventful boundary that general relativity predicts, but instead a wall of high-energy radiation that would incinerate anything trying to cross. A proposal that, if correct, would mean that everything we described in the previous chapters about the gentle crossing of the event horizon is wrong. None of these proposals has been confirmed. None has been definitively ruled out. The question of what happens to information that falls into a black hole, and by extension, what happened to you, is one of the deepest open problems in physics. It sits at the intersection of gravity and quantum mechanics, the two pillars of modern physics that have never been successfully unified into a single theory. Solving the information paradox may require that unified theory. Building that theory may be the work of the next century, and until it is built, the question of whether you, in any meaningful informational sense, survive the crossing of the event horizon will remain unanswered. What the distant observer sees is simpler, and in its simplicity more haunting. A brief reddening, a rapid fade, silence, and then a black hole that is, by an imperceptible amount, slightly heavier than it was before. There is one more thing you would have seen falling toward the event horizon that we have not yet discussed, and it may be the most beautiful and the most terrible thing that physics permits a conscious being to witness. Look up. As you fall, the circle of light above you, the compressed disk containing every photon from the external universe, is not merely shrinking, it is changing color. The light arriving from the universe outside is being gravitationally blue shifted, the inverse of the redshift that stretches your outgoing photons to invisibility. Photons falling inward toward you gain energy as they descend through the gravitational well, their wavelengths compressed, their frequencies climbing. Infrared becomes visible light. Visible light becomes ultraviolet. Ultraviolet becomes X-ray. The stars above you, which have been crowding together into that narrowing circle since you passed the photon sphere, are getting brighter and bluer with every second that passes on your wristwatch, and they are getting faster. This is the temporal counterpart to the spatial compression. The universe outside the black hole is aging more quickly relative to your local time as you descend deeper into the gravitational well. We covered this in the context of time dilation. Your clocks slow relative to the outside, which is equivalent to saying that the outside clocks speed up relative to yours. At the photon sphere, the factor was moderate. Closer to the horizon, it climbs steeply. And what this means, in terms of the light reaching your eyes, is that the photons arriving from the outside universe carry information from an increasingly distant future. Each successive photon that reaches you was emitted later in the external universe's timeline than the one before. The stars in that circle above you are not just brighter and bluer, they are older. You are watching the universe age in fast forward, compressed into a shrinking aperture of blue-white light directly overhead. How much of the future you could theoretically see depends on the specifics of your trajectory, the mass and spin of the black hole, and several technical assumptions about the optical properties of the infalling environment. The popular version of this idea, that a falling observer sees the entire future of the universe flash before their eyes at the moment of crossing the event horizon, is an exaggeration, or at least an oversimplification. In a strict Schwarzschild black hole, the light you receive at the moment of crossing comes from a finite, though very large span of the universe's future. You do not see the literal end of time, but you see far. Depending on the geometry, you could witness millions or billions of years of external evolution compressed into the final seconds of your descent. Stars burning through their fuel cycles, galaxies drifting apart, the slow reddening of the cosmic background as the universe expands and cools. For a rotating black hole, a Kerr black hole, which is what Sagittarius A star actually is, the situation is more complicated and, in certain limiting cases, more extreme. Some theoretical analyses of observers falling into rapidly spinning black holes suggest that the blue shift at the inner horizon can become genuinely infinite, meaning that the observer would, in the final instance, receive light from the entire future history of the external universe. Every photon that will ever be emitted, arriving in a single overwhelming burst. The mathematical models that produce this result involve idealized conditions that may not hold in a real astrophysical black hole. Perturbations, infalling matter, and quantum effects would likely modify the picture, but the basic phenomenon is physically grounded. You are falling into a region where your local time is radically compressed relative to the external universe, and the light reaching you carries the evidence of that compression. Think about what this means in experiential terms. You are falling feet first toward the center of a 4 million solar mass black hole. Below you, darkness, the total photon-free darkness of the interior, where space-time points inward in every direction and the singularity waits as a moment rather than a place. Above you, a disk of light that contains the visible universe, shrinking and blue shifting, the stars within it aging at a rate that accelerates with every heartbeat. The accretion disk, already distorted beyond recognition, wraps around the edge of this disk in a bright, smeared band. And inside that circle, compressed into an area not much larger than the full moon as seen from Earth, you can see the future, not metaphorically, physically. The photons arriving at your retina left their sources years, centuries, millennia from now in the external timeline, and they have been blue shifted into the visible spectrum by the gravitational field, arriving with enough energy to be seen and with enough temporal displacement to be genuinely prophetic. You are watching the stars die. Not all at once, and not as a sudden cataclysm, but as a time-lapse played at a speed dictated by the gravitational gradient through which you are falling. The main sequence stars, the ones like our Sun, burning hydrogen steadily, swell into red giants as their fuel depletes, their outer layers expanding and cooling before being shed into space as planetary nebulae, leaving behind white dwarfs that cool and fade over billions of years. The more massive stars detonate as supernovae, brief flares in the compressed timeline, their cores collapsing into neutron stars or, and there is something recursive about this, into new black holes. The galaxies themselves drift apart as the expansion of the universe carries them beyond each other's observable horizons. The cosmic microwave background, the faint afterglow of the Big Bang, stretches and cools toward absolute zero. The lights go out, one by one, in a sequence that spans trillions of years in the external timeline and arrives at your eyes in a cascade of blue-shifted photons that lasts, on your wristwatch, a matter of seconds. And then the disk closes. The light narrows to a point. The point dims to nothing. And the last thing you see, the final image carried by the final photon to reach you from outside, is darkness. Not the darkness of a night sky full of stars you cannot quite resolve. The darkness of a universe that has used up its light. Whether that final image is real, whether the photons from the genuine heat death of the universe actually reach a falling observer, or whether the mathematical idealization breaks down long before that point, is a question that depends on details of quantum gravity that no one has yet worked out. The conservative answer is that you would see a great deal of the universe's future, but not all of it. The speculative answer is that you might, in the last fraction of a second, receive the entire history of the cosmos compressed into a single burst of light. Either way, the qualitative experience is the same. You witness the universe age and darken from a vantage point that no other location in space-time could provide. And you witness it in the final moments of your own existence, in a body that has already crossed the boundary from which no return is possible. There is something in this image that resists the language of dread. A person, falling beyond rescue, watching the life of the universe unfold above them in a compressed bloom of light, watching everything that will ever happen, all the births and deaths of stars, all the slow dispersal of galaxies, all the long cooling of the cosmos toward its final temperature before the disk closes and the light goes out. It is catastrophic, and it is transcendent, and it is, depending on how you hold it in your mind, either the loneliest thing imaginable or the most intimate, because in that moment you are the only conscious being. If consciousness still functions, if the nervous system is still intact, who has ever seen the universe from this angle? You are seeing it whole, you are seeing it finished, and then you are not seeing anything at all. In 1976, Stephen Hawking published a paper that broke physics, not immediately and not in a way that most physicists recognized at the time. The paper, titled Breakdown of Predictability in Gravitational Collapse, appeared in Physical Review D and made a claim so stark that it took the community years to fully absorb its implications. Hawking argued that black holes destroy information, not in the way a fire destroys a book, where the information is technically still present in the arrangement of the ash and smoke and heat, recoverable in principle if you could track every particle, but genuinely, irretrievably, fundamentally. A quantum state that falls into a black hole, Hawking argued, is converted through the process of Hawking radiation into thermal noise, random, featureless, carrying no imprint of what went in. The black hole eventually evaporates, the radiation disperses, and the information that described the original quantum state is gone, not hidden, not scrambled, gone. This matters because quantum mechanics, at its deepest level, is built on the assumption that information is conserved. The technical term is unitarity, the principle that the quantum evolution of a system is reversible, that the present state of the universe contains, in principle, enough information to reconstruct any past state. Unitarity is not an optional feature of quantum mechanics. It is load-bearing. Remove it, and the mathematical structure of the theory collapses. Probabilities stop adding up to 1. Predictions become impossible. The entire framework, the framework that describes atoms, molecules, chemistry, electronics, the behavior of every particle in the standard model ceases to function as a coherent theory. Hawking was saying that black holes violate this principle, and he was saying it not as speculation but as a consequence of careful calculation, applying the known laws of quantum field theory to the curved space-time around a black hole. His derivation of Hawking radiation, the discovery that black holes emit a faint glow of quantum particles, slowly losing mass and eventually evaporating entirely, was and remains one of the most celebrated results in theoretical physics. The problem was the corollary. If the radiation is truly thermal, truly featureless, then the information about everything that ever fell in is erased when the black hole finishes evaporating. General relativity says nothing can escape through the event horizon. Quantum mechanics says information cannot be destroyed, and the black hole sits at the intersection, obeying both theories in ways that make them contradict each other. For years, the debate was surprisingly one-sided. Most physicists who worked on quantum gravity, particularly those in the string theory community, believed that unitarity would survive, that information was somehow preserved, and that Hawking's argument had a flaw that would eventually be identified. Hawking himself characteristically dug in. He bet against unitarity's survival, wagering an encyclopedia against John Preskill of Caltech that information was genuinely lost. The bet was made in 1997. It would take 7 years to be settled, and the settlement would raise more questions than it answered. The firewall argument arrived in 2012, and it made everything worse. 4 physicists, Ahmed Almheri, Donald Maroff, Joseph Polchinski, and James Sully, collectively known by the acronym AMPS, published a paper arguing that 3 widely held assumptions about black holes could not all be true simultaneously. The assumptions were, first, that the event horizon is a smooth, uneventful boundary that a falling observer can cross without noticing, the prediction of general relativity that we have been relying on throughout this documentary. Second, that the Hawking radiation emitted by a black hole is entangled with the black hole's interior in a specific way required by quantum mechanics. And third, that the Hawking radiation emitted late in a black hole's life is entangled with the radiation emitted earlier, which is required for information to be recovered from the radiation after the black hole evaporates. The problem is a property of quantum entanglement called monogamy. A quantum system can be maximally entangled with only one other system at a time. If the late Hawking radiation must be entangled with both the interior of the black hole and the early radiation, then something has to give. AMPS argued that what gives is the first assumption, the smooth event horizon. If you enforce unitarity and monogamy, they argued, the entanglement between the infalling particle and the outgoing radiation must be broken at the event horizon, and breaking that entanglement releases energy, a great deal of energy, enough energy to create a wall of fire at the event horizon, a firewall that would incinerate anything attempting to cross. If the AMPS argument is correct, then the experience described in the earlier chapters of this documentary, the gentle crossing, the weightless passage, the silent transition from outside to inside, is wrong. There is no gentle crossing. There is a wall of radiation at the event horizon, and you burn before you ever reach the interior. The singularity becomes irrelevant because you never get there. You end at the boundary. The physics community did not react well to this suggestion. The equivalence principle, Einstein's insight that free fall is locally indistinguishable from the absence of gravity, is one of the foundations of general relativity. Suggesting that the event horizon violates it is, for many physicists, roughly equivalent to suggesting that the Earth might be flat after all, not impossible in principle, but deeply offensive to the theoretical structure that has been painstakingly built over the past century. Responses came from every direction. Leonard Susskind and Juan Maldacena proposed ER equals EPR, the idea that quantum entanglement and spatial connectivity through wormholes are the same phenomenon, which would allow the late radiation to be entangled with the interior without violating monogamy because the interior and the radiation are geometrically connected. Others proposed that the interior of the black hole is described by the same quantum degrees of freedom as the radiation, eliminating the apparent conflict by identifying the two systems as one. Others argued that the computational complexity of actually verifying whether the entanglement is broken would exceed the resources available to any physically realizable experiment, making the firewall question not wrong but unanswerable in practice. And in July 2025, the physicist Raphael Bousso published a paper arguing that any attempt to maintain a smooth event horizon while also preserving information requires a breakdown of general covariance, one of the most basic symmetry principles of general relativity, far from the black hole, in regions of weak gravity where the theory has been tested and confirmed to extraordinary precision. The paper did not resolve the paradox, it sharpened it. The options, Bousso argued, are all unpalatable. Either the event horizon is violent, or general relativity breaks in places we thought it was safe, or something else entirely is happening that we do not yet have the language to describe. This is the state of the question as of today. The information paradox is not a historical curiosity or a philosophical puzzle. It is an active crisis in theoretical physics, and it touches everything. The nature of space-time, the validity of quantum mechanics in gravitational contexts, the question of whether the interior of a black hole is even a meaningful concept, and the question, which should sound familiar by now, of whether a person who falls into a black hole is destroyed or preserved. Hawking conceded the bet in 2004, announcing at a conference in Dublin that he now believed information was preserved. He handed Preskill a baseball encyclopedia, the agreed-upon stakes. Preskill accepted it, but noted publicly that he was not entirely sure Hawking had given a convincing reason for the concession. The mechanism of information preservation remained unclear. Hawking's proposed solution, involving a sum over topologies in the gravitational path integral, was technical, incomplete, and not universally accepted. He died in 2018 without seeing the paradox resolved. The encyclopedia sits on Preskill's shelf. The question it represents is still open. Nothing lasts forever, not even the things that were built to swallow forever. Hawking's most celebrated discovery, more celebrated in the end than the paradox it created, was that black holes are not permanent. They radiate, slowly, faintly, at a temperature so low that for any black hole we have ever observed, the radiation is completely undetectable against the cosmic microwave background, the faint thermal afterglow of the Big Bang that fills all of space with photons at a temperature of about 2.7 Kelvin. A black hole with the mass of Sagittarius A star has a Hawking temperature of roughly 14 trillionths of a Kelvin, 14 times 10 to the minus 12 degrees above absolute zero, colder than anything that has ever been measured in a laboratory, colder than the void between galaxies, colder than the background radiation by a factor of about 200 billion. In the current universe, a supermassive black hole does not lose mass through Hawking radiation. It gains mass because the energy it absorbs from the cosmic microwave background alone exceeds what it emits. The radiation is real, but it is, for now, irrelevant. For now, the universe is expanding. As it expands, the cosmic microwave background cools. It has been cooling since the Big Bang, dropping from a temperature of billions of degrees in the first seconds to its present value of 2.7 Kelvin over the course of 13.8 billion years, and it will continue to cool as the expansion continues. At some point in the distant future, so distant that the number requires scientific notation to write and defies analogy to comprehend, the background temperature will drop below the Hawking temperature of the largest supermassive black holes. When that happens, the black holes will, for the first time, be hotter than their environment. They will begin to radiate more energy than they absorb. They will begin to shrink. The shrinking is almost unimaginably slow. A black hole with the mass of our Sun, if such a thing could be formed, which current astrophysics suggests it cannot through stellar collapse alone, would take approximately 10 to the 67th years to evaporate completely through Hawking radiation. That number deserves a moment of stillness. 10 to the 67 years. The current age of the universe is about 10 to the 10th years. 10 billion years, roughly. The time required for a solar mass black hole to evaporate is not 1,000,000 times longer than the age of the universe, or 1,000,000,000 times, or 1,000,000,000,000 times. It is 10 to the 57 times longer. Written as a ratio, the age of the universe compared to the evaporation time of a single solar mass black hole is approximately the same as the ratio of a single atom to the entire observable universe. These are numbers that the human brain is not equipped to hold, and the appropriate response to them is not understanding but a kind of cognitive surrender, an admission that the number exists and has meaning, and that you will never, in any experiential sense, know what it refers to. For Sagittarius A star, with its 4.3 million solar masses, the evaporation time is proportionally longer. Hawking radiation timescales go as the cube of the mass, double the mass, and the evaporation time increases by a factor of 8. For the supermassive black holes at the centers of the largest galaxies, objects like TON 618, estimated at 66 billion solar masses, the evaporation time pushes toward 10 to the 100th years, a number so large that writing it out in full would require more digits than there are atoms in the observable universe. But it is finite. That is the point. It is finite. Every black hole, no matter how massive, has a lifespan. The lifespan is absurdly, incomprehensibly, almost offensively long, but it ends. Hawking radiation is patient. It does not hurry. It does not care that the process will take longer than any other process in the physical universe. It simply continues, photon by photon, quantum by quantum, eroding the mass of the black hole the way that rain erodes a mountain, except that the mountain is the size of a solar system and the rain falls 1 drop per epoch. And as the black hole shrinks, something curious happens. Its temperature rises. This is the counterintuitive property that makes Hawking radiation so strange. Smaller black holes are hotter. The temperature is inversely proportional to the mass, so as the black hole loses mass, it gets warmer, which means it radiates faster, which means it loses mass more quickly, which makes it hotter still. The process accelerates. For most of the black hole's life, the evaporation is so slow as to be essentially non-existent. The overwhelming majority of that 10 to the 67th year lifespan is spent in a state of near equilibrium, barely radiating, barely shrinking, waiting. But in the final stages, the acceleration becomes dramatic. The last 10% of the mass is shed more quickly than the first 90%, the last 1% faster still, and in the very final moments, the last fractions of a second, the black hole's temperature spikes to extraordinary values, its radiation output surges, and the remaining mass is converted to energy in a burst that, for the briefest of instants, is visible. Then it is gone. The event horizon contracts to nothing. The singularity, if it existed in any physical sense, which remains an open question, ceases to exist. The region of space-time that was the interior of the black hole rejoins the rest of the universe, though rejoins is a word that carries more certainty than the physics can support, since we do not know what state the interior was in before the evaporation completed. What remains is a puff of radiation expanding outward at the speed of light, carrying with it the total energy that the black hole had accumulated over its lifetime. Every star it swallowed, every planet, every photon of the cosmic microwave background, every hypothetical person who fell through its event horizon, all of it converted to a fading spray of particles that disperses into the void and eventually thermalizes with the background radiation of a universe that has by this point been expanding and cooling for so long that the stars stopped forming trillions of years ago. The last black holes to evaporate will be the most massive ones, the supermassive monsters at the centers of galaxy clusters, objects that will have spent the better part of 10 to the 100th years as the last organized structures in a universe that has long since gone dark. When the final one evaporates, there will be nothing left that could reasonably be called a structure. No stars, no planets, no atoms bound into molecules, just a thin cooling bath of photons and elementary particles, drifting apart in an expanding space, approaching but never quite reaching thermal equilibrium for a length of time that makes the black hole era itself look brief. And the universe will not remember that any of this happened. There will be no record, no trace that can be read. The information paradox will have resolved itself one way or another. Either the information was encoded in the Hawking radiation all along, or it was lost, or something else happened that we cannot currently imagine. But whatever the answer, there will be no one left to learn it. The last photon from the last black hole will propagate through empty space at the speed of light, forever carrying the final whisper of an object that once consumed everything that came near it, and there will be nothing in its path to absorb it, nothing to detect it, nothing to know that it was ever emitted. Silence, expanding at the speed of light in all directions, without end. We have, across the length of this documentary, described a journey that no human has taken and no instrument has recorded. Everything we have said about the experience of falling into a black hole, the visual distortions, the time dilation, the crossing of the event horizon, the spaghettification, the encounter with the singularity, has been derived from mathematics, specifically from solutions to Einstein's field equations of general relativity, supplemented by results from quantum field theory in curved space-time. The predictions are internally consistent, physically motivated, and supported by every indirect observation we have been able to make, from the orbits of stars around Sagittarius A star to the gravitational wave signatures of merging black holes detected by LIGO and Virgo. The mathematics has been tested at every boundary we can reach, and it has not failed, but it has limits. And before this documentary comes to its close, those limits deserve to be named plainly, because the distance between what we know and what we pretend to know is, in the case of black holes, unusually large. We do not know what the singularity is. General relativity predicts infinite curvature at r equals 0, a point where density, tidal forces, and the curvature of spacetime all diverge to infinity. In physics, infinities are almost always a sign that the theory has been pushed beyond its domain of validity, the way Newtonian mechanics produces nonsensical predictions at velocities approaching the speed of light. The singularity is probably not a physical infinity, it is probably a marker, a flag planted by general relativity at the edge of its own competence, indicating that a deeper theory is needed. That deeper theory is quantum gravity, the long-sought unification of general relativity and quantum mechanics, and it does not yet exist. We have candidates: string theory, loop quantum gravity, asymptotic safety, causal set theory, but none of them has produced a testable prediction that distinguishes it from the others, and none of them provides a definitive answer to the question of what replaces the singularity when quantum effects are properly accounted for. Some of these approaches suggest the singularity is smoothed out, replaced by a region of extremely high but finite curvature, a Planck-scale core where quantum gravitational effects halt the collapse before it reaches infinity. Others suggest the singularity is a transition, a bridge to another region of spacetime, possibly a new universe, possibly a white hole that ejects matter rather than consuming it. The physicist Lee Smolin has proposed that each black hole singularity gives birth to a new universe with slightly different physical constants, a kind of cosmological natural selection. Roger Penrose suggested that singularities might play a role in resetting the universe's entropy at the end of each cosmic cycle, in a model he called conformal cyclic cosmology. These ideas are speculative in the deepest sense, not merely unconfirmed, but currently unconfirmable because the singularity is hidden behind an event horizon from which no information can escape to be tested. We do not know with certainty what the event horizon feels like. The standard prediction of general relativity, that a freely falling observer crosses the event horizon without noticing, is derived from classical theory and may not survive the inclusion of quantum effects. The AMPS firewall argument suggests the crossing could be violent. Other proposals suggest it could be strange in ways that neither classical nor firewall pictures capture, that the event horizon might be a fuzzy quantum mechanical boundary rather than a sharp geometric surface, or that the concept of an interior might not be well defined in a complete theory of quantum gravity. The fact that we describe the crossing as smooth and silent throughout this documentary reflects the best prediction of our best current theory. It does not reflect certainty. We do not know whether information is preserved. The information paradox, as we discussed, remains open. Recent work on entanglement islands and the island formula has generated optimism that unitarity survives, that the page curve, which describes how entanglement entropy should behave during black hole evaporation if information is preserved, can be reproduced using semi-classical gravity. These results are genuinely encouraging, but they rely on specific theoretical assumptions, particularly the framework of the ADS/CFT correspondence, and it is not clear whether they apply to the kind of black holes that exist in our universe, which live in an expanding, positively curved spacetime, rather than the negatively curved anti-de Sitter space where the calculations are most tractable. We do not know whether the interior of a black hole is real in the sense that the word real usually implies, whether there is a physical region of space-time behind the event horizon that persists as a well-defined geometric entity, or whether the interior is better understood as a kind of theoretical projection, a mathematical continuation of the exterior solution that may not correspond to anything a future theory of quantum gravity would recognize. This is perhaps the most uncomfortable item on the list, because it questions not a detail but the premise, the assumption, implicit throughout this documentary, that there is an inside to fall into. These are not weaknesses in the narrative we have told. They are the honest boundaries of physics in its current state. The mathematics of general relativity provides a precise and self-consistent description of what happens to a body falling into a black hole, and that description is the foundation of everything we have discussed. But general relativity is a classical theory, and the interior of a black hole is a quantum gravitational environment, and the relationship between the classical description and the eventual quantum description is unknown. We are in the position of someone who has drawn a beautiful, accurate map of a coastline using the best available surveying tools, while knowing that the ground beneath the coastline may be shifting in ways those tools cannot detect. What we do know is this: black holes exist. Their masses have been measured, their event horizons have been imaged, their gravitational waves have been recorded. The predictions of general relativity, in every domain where they can be tested, have been confirmed to extraordinary precision. The mathematics describes something real. The question, the only question, is whether the mathematics describes the inside as accurately as it describes the outside. And that question, for now, belongs to the silence on the other side of the event horizon. The silence we cannot penetrate, cannot record, cannot bring back. The same silence that has been there since Schwarzschild first found it in his equations, sitting in a trench in 1915, writing a letter to Einstein while the guns fired overhead. So what do we know? We know that in 1915, a soldier on the Eastern Front solved a set of equations that described the curvature of spacetime around a spherical mass, and that the solution contained a radius where the mathematics broke in a way that nobody could explain. We know that 23 years later, a young physicist in Berkeley proved that the breakdown was not a flaw, but a prophecy, that stars above a certain mass have no choice but to collapse past that radius and keep collapsing forever into a region from which nothing returns. We know that for another 3 decades, most of the physics community looked away, unable or unwilling to accept what the equations were saying. We know that in 1967, someone finally gave the thing a name, and the name made it real in a way the mathematics alone could not. We know that black holes exist. We have weighed them by watching stars orbit their darkness. We have heard them collide, their gravitational waves washing through the fabric of space-time and arriving at detectors on Earth as a faint chirp, a vibration smaller than the width of an atom. We have photographed their shadows, the absence of light at their centers, ringed by the glow of gas heated to hundreds of millions of degrees. Sagittarius A star, the one we have been falling into for the length of this documentary, sits 27,000 light-years away at the center of our galaxy, 4.3 million times the mass of the Sun. Its event horizon a dark sphere about 17% as wide as the distance from the Earth to the Sun. It is there. It has always been there, or at least it has been there for as long as the Milky Way has had a center worth speaking of. And we know with reasonable confidence what it would be like to fall in. The approach would be quiet. Gravitational lensing would warp the stars into arcs and rings. The accretion disk would glow with a light that shifts and distorts as you get closer, Doppler boosted and gravitationally bent into shapes that no earthbound geometry could produce. At the photon sphere, you would see the back of your own head, reflected around the black hole by light traveling in closed loops. The sky would split, the universe above, darkness below, and as you continue to fall, the universe would compress into a shrinking circle of blue-white light overhead, growing brighter and faster, aging in fast forward, showing you the future of a cosmos you're about to leave. The event horizon would pass without sensation. No wall, no light, no sound. Free fall feels like weightlessness, and the equivalence principle holds even here, at the boundary of the most extreme gravitational environment in the universe. You would not know you had crossed until you checked the math, and by then, checking the math would be a luxury measured in seconds, 12.8 of them to be precise. In those seconds, the tidal gradient across your body would steepen from gentle to catastrophic. The space between your atoms would be stretched along the radial direction and compressed from the sides, and the process that physicists named spaghettification would convert your body from a three-dimensional structure into a one-dimensional thread falling toward a singularity that is not a place but a time, a moment you cannot avoid the way no one avoids tomorrow. And from the outside, none of this would be visible. A distant observer would see you slow, redden, and fade at the event horizon, your image dimming exponentially until the last photon fell below the threshold of detection, leaving behind nothing but a black hole that is, by an imperceptible amount, heavier than it was before. Two realities, both true, both emerging from the same set of equations, written by a man who believed they described the curvature of space around ordinary stars, refined by a generation that wanted nothing to do with the implications, and finally accepted by a scientific community that had no choice, because the equations matched every observation, every measurement, every gravitational wave signal that the universe sent our way. We do not know what happens at the singularity. We do not know whether the event horizon is as gentle as general relativity predicts, or whether quantum effects transform it into something else, a firewall, a fuzz, a boundary condition in a theory we have not yet written. We do not know whether the information that describes a human life survives the crossing in any recoverable form, or whether it is erased, or whether the question itself will one day be recognized as malformed, the way asking about the temperature of justice is malformed. These are open problems. They sit at the intersection of gravity and quantum mechanics, the two deepest descriptions of nature that human beings have ever produced, and they refuse to fit together. Somewhere, right now, someone is working on them. A graduate student staring at a whiteboard at 2 in the morning, an equation that almost closes but doesn't. A postdoc running a simulation on a cluster of GPUs, watching a model of an evaporating black hole for signs that the page curve bends the way it should. A senior physicist giving a talk to a half-empty seminar room, proposing a modification to the event horizon that will be debated for 10 years and may turn out to be wrong. They are doing what Schwarzschild did in the trenches, what Oppenheimer did in Berkeley, what Hawking did in Cambridge, reaching toward a piece of the universe that does not want to be understood and refusing to stop reaching. That refusal is, in some ways, the strangest part of this story, stranger than the photon sphere, stranger than the singularity, stranger than the reversal of space and time inside the event horizon. The universe does not care whether we understand it. It has been running its black holes for billions of years without an audience, collapsing stars and swallowing light in galaxies so distant that their photons will never reach us. The cosmic machinery is indifferent. It does not need to be witnessed, interpreted, or named. And yet we witness, interpret, and name it. We write equations in trenches. We build planet-sized telescopes. We run simulations on supercomputers and argue about firewalls in seminar rooms. We look at the darkness, the specific, measurable 4.3 million solar mass darkness at the center of our own galaxy, and we ask what it would feel like to fall in. There are 2 trillion galaxies in the observable universe. Most of them have a supermassive black hole at their center. The nearest one to us is 27,000 light-years away, which is close enough to photograph but far enough that it poses no threat to anything on Earth, now or ever. The light from the stars you can see tonight has been traveling for years, decades, centuries, some of it since before you were born, all of it from a universe that was slightly different when it left. By the time it reaches your eyes, the stars that sent it have moved, aged, and in some cases ceased to exist. You are always looking at the past. You are always looking at light that left its source when the source was somewhere else, doing something else, being something else. This is not a limitation of your instruments. It is a property of the universe. Everything you see is a memory. And in that sense, the night sky is not so different from the inside of a black hole. Both are made of light that carries information about things that are gone. Both are vast. Both are silent. And both are, if you let them be, the kind of darkness you can fall asleep inside. The black hole at the center of the Milky Way has been there for billions of years. It will be there for incomprehensible trillions more, slowly gaining mass from the accretion of gas and the occasional unlucky star, its hawking radiation so faint that it will not begin to lose mass until the cosmic microwave background has cooled to a temperature so close to absolute zero that the difference is meaningless. And then, across a span of time that dwarfs the entire history of the universe to date, it will evaporate, photon by photon, quantum by quantum, until the event horizon contracts to nothing and the last whisper of radiation disperses into a cosmos that has long since gone dark. It will not know that we were here. It will not know that someone, once, looked at it from 27,000 light years away and asked what it would be like to fall in. It will not know that a soldier in a trench solved its equations while the shells fell, or that a physicist in Berkeley proved those equations right while the world prepared for war, or that a man in a wheelchair in Cambridge discovered that it would eventually die. None of that will matter to the black hole, but it matters to us. It matters that we asked. It matters that we reached towards something we cannot touch, with instruments we built from the ground up, using a language of mathematics that we invented to describe a universe that never asked to be described. And it matters that tonight, in the dark, listening to this, you know a little more about what the darkness contains than you did an hour ago. The universe is very large, the darkness is very deep, and you are very small. But you looked. That counts for something.